Hello there and welcome to Science for Sleep, the quiet corner of the universe where big questions take their time and your thoughts can settle like dust in a sunbeam. Tonight we're going to drift into something that sounds almost like science fiction, but has been taken very seriously by some of the brightest minds in physics. It's called string theory, and at its heart is one extraordinary suggestion that everything you've ever known, every star, every atom, and even you, might be nothing more than vibrations in an invisible cosmic instrument. Now that might sound like the kind of late-night thought that sneaks in just as you're trying to fall asleep, but don't worry. This isn't going to be overwhelming. In fact, it's the perfect place for it. If the universe really is music, we've got all the time in the world to listen. Before we dive in though, I'd love to know where you are tonight. Are you curled up under a blanket in a quiet room? Or maybe you've got the low hum of city life outside your window? And just for fun, what time is it where you are? It's oddly fitting to talk about vibration, about rhythm, while we're all scattered across different clocks, each of us pressing play on this conversation at our own tempo. If you find this little exploration soothing, or if you just enjoy having something thoughtful and unhurried to fall asleep to, I'd be ever so grateful if you'd like the video and maybe subscribe. It helps this little pocket of calm reach more people who might need it. And if by some chance this keeps you awake, well, at least you'll learn a few things about how reality might secretly be strumming itself into existence. So, settle in, breathe a little slower, and let's begin. String theory didn't start as a grand plan to explain everything. In fact, it began almost by accident. Back in the late 1960s, physicists were wrestling with one of the biggest puzzles in science: how to describe the forces of nature in a single framework. They had theories for electromagnetism and the nuclear forces that hold atoms together, but gravity stubbornly refused to fit in. At the time, a few researchers noticed that an odd mathematical formula they were studying seemed to describe tiny particles, as if they weren't points at all, but tiny, one-dimensional strings. These weren't strings like guitar strings or the ones you use to tie a package. They were unimaginably small, far smaller than atoms, vibrating in patterns so quick and subtle that to us they'd look like nothing at all. And yet, hidden in those tiny vibrations might be the blueprint for everything. This is the part that feels both outrageous and strangely elegant. In the old view of physics, the universe is made of particles, electrons, quarks, neutrinos, the whole zoo of fundamental building blocks. But in string theory, those so-called particles are just different notes played by the same underlying string. Change the vibration, you change the particle. One pattern hums as an electron, another as a photon, and yet another as the mysterious graviton, the hypothetical particle of gravity that has eluded scientists for decades. In this way, string theory doesn't just describe matter, it gives it a kind of hidden music. It's almost impossible to picture because these strings, if they exist, are 100 billion times smaller than the nucleus of an atom. You could never hope to see one, not even with the most powerful microscope humanity could dream up. But mathematically, they fit. The equations are complicated, breathtakingly so, but within them is the suggestion of a universe that isn't built from rigid little bricks of matter. It's woven from vibrating threads, so small and so fast they blur into the reality we take for granted. Now, before you imagine the universe turning into some cosmic rock concert, it's worth saying this vibration isn't sound the way we normally experience it. It's not something you could hear. Sound needs air or water, or some kind of medium to carry it, and the world these strings live in is deeper than that. Their vibrations are patterns of energy, oscillations in the most fundamental fabric of existence. If reality does have a soundtrack, it's one we feel more in the equations than in our ears. But what makes this idea so captivating isn't just its strangeness. It's that it might finally unite the two halves of physics that have been glaring at each other across the scientific table for over a century. On one side, you have quantum mechanics, the rulebook for the very small, where particles pop in and out of existence and uncertainty reigns supreme. On the other side, you have general relativity, Einstein's grand description of gravity and the geometry of space and time itself. Both of these theories work beautifully in their own domains, but they hate each other. Try to combine them, and the math breaks down. String theory offers a kind of truce. By replacing point-like particles with tiny vibrating strings, it softens the infinities that plague other attempts to merge these two worlds. Suddenly gravity doesn't misbehave. Quantum mechanics and relativity stop fighting quite so violently. For a brief, tantalizing moment, everything seems to hum together. Of course, there's a catch, because there's always a catch. For the equations to work, the universe can't just have the 3 dimensions of space and one of time that we're familiar with. String theory demands more. 10 dimensions, sometimes 11, depending on the version. These extra dimensions aren't ones you can walk through. They're curled up so tightly, so minutely, that we never notice them. Like tiny hidden hallways folded into every point in space, too small for even the smallest particle of light to slip through. And yet, if string theory is right, those hidden dimensions are just as real as the length, width, and height of the room you're sitting in. Everything we see would just be the surface of a far more elaborate structure, one that stretches far beyond our senses. It's the kind of thing that can make your mind do a quiet somersault, but strangely, it doesn't feel chaotic. It feels ordered. If you've ever heard a violinist draw a bow across a string and play a perfect steady note, there's a kind of stillness to it, even though the string is moving furiously. That's how string theory sometimes feels. Behind the wild mathematics and the almost absurd implications is a deep, almost tranquil sense that everything fits. And yet, for all its beauty, string theory remains unproven. No one has seen a string. No experiment has yet confirmed their existence. To test the theory directly, we'd need an accelerator so powerful it would make the Large Hadron Collider look like a toy. So instead, physicists look for indirect clues, little hints in the mathematics and in the behaviour of the universe that might suggest strings are really there. Some critics argue it's not science at all, because without clear predictions that we can test, it risks turning into philosophy dressed in equations. But others would say the history of physics is full of ideas that began as untestable dreams and only later found their proof. And maybe that's part of the appeal. There's something deeply human about it. The thought that the universe might be a single instrument, playing itself across dimensions we'll never walk through, is both audacious and strangely comforting. If it's true, then you, me, every star and planet, every atom in the air you're breathing right now, we're all notes in the same song. And if that's the case, maybe the question isn't just whether string theory is right. Maybe it's whether we've been listening closely enough all along. Have you ever wondered, as you lie in bed at night, listening to the quiet hum of the world around you, if there's something more? Something beneath the surface just out of reach, waiting for us to understand? We go about our lives day to day, surrounded by the rhythm of time, the ticking of clocks, the pulse of our hearts. But every so often there's a question that slips through the cracks of our routine, lingering at the edges of our thoughts. For some, it's the question of where the universe came from. For others, it's the question of what happens after we die. But for a select few, there's another question, a quieter, more persistent question that refuses to go away. What if the universe itself is nothing more than vibration? It's a question that doesn't have an easy answer. In fact, it may not even have an answer that we can grasp right now. It might be one of those questions that sits at the edge of science, just out of reach, teasing us with its possibility but never quite letting us touch it. And yet, the more we look at the world around us, the more it starts to make sense. What if, just as sound waves vibrate through the air to reach our ears, Everything we see and touch is a pattern, a frequency, a ripple in a vast cosmic ocean. The idea of vibration is nothing new. Ancient cultures believed that the universe was built on sound, that everything from the stars to the earth itself was a kind of song. In the East, there's the concept of Om, the primordial sound said to be the source of everything. In the West, the ancient Greeks thought of the cosmos as a grand harmony, each planet moving in its own unique rhythm, creating a symphony of cosmic music. For them, it was a way to explain the order of the universe, its movements and its patterns. They could feel the music in the stars, the pulse of existence in everything around them. But as we learned more about the universe, we realized that the song we once thought was metaphorical might just be more real than we imagined. String theory, with its elegant mathematics, suggests that the very fabric of reality might indeed be woven from vibrations, each vibration corresponding to a different particle, a different force, a different part of the world. The theory doesn't just rely on metaphors, it's built on the idea that the fundamental particles of nature aren't little hard balls bouncing around in space, but tiny strings that vibrate, each in its own way, creating everything we see. Think about that for a moment. What if everything, the earth beneath your feet, the air in your lungs, the stars in the sky, isn't just made of solid matter, but is instead a pattern, a note in a cosmic symphony? It's a concept that stretches the imagination, but it also feels strangely familiar. After all, we experience vibration every day. When you hear a song, you feel the beat in your chest, don't you? When you touch a surface, the molecules within it are vibrating, even if you can't feel it. Sound itself is nothing more than vibrations in the air, travelling at different frequencies. Light, too, can be described as a vibration, a wave of energy oscillating through space. If everything around us is vibrating at its own frequency, then it follows that the universe is alive with movement. And if the universe is alive with movement, then perhaps that means everything is interconnected, each vibration linked to the next. It's almost as if we're all playing our part in the same orchestra, even if we don't fully understand the music. But there's a deeper question here, one that ties back to the heart of string theory. If everything is vibration, then what happens when those vibrations stop? It's a difficult question to answer, because it touches on the very nature of existence itself. If the universe is a cosmic song, what would it mean if the song were to stop playing? Would the stars cease to shine? Would the planets stop their dance around the sun? Would we cease to exist? We don't know, of course. But what string theory offers is a framework, a way to think about these questions in a new light. And it's a framework that might one day help us answer the most fundamental question of all. What is the nature of reality? Perhaps we've been looking for the wrong answers all along. Instead of searching for particles that can be split into smaller and smaller pieces, what if we've been missing the bigger picture? What if the key to understanding the universe isn't in what we can see or touch, but in the invisible patterns that underlie everything we experience? And that's where string theory comes in. It doesn't just offer a new way to look at particles and forces, it suggests that the entire structure of reality, the very fabric of space and time, might be woven from the same vibrating strings. It's a bold idea, and one that's still far from being proven, but it's an idea that can't be ignored, because if it's true, then it means that everything we know is just a single note in a much larger symphony. So the question that won't stay quiet, the question of whether the universe is just vibration, becomes more than just an abstract thought experiment. It becomes a question that could reshape the very way we understand the world. And maybe that's the beauty of it. In a universe that's constantly shifting, vibrating and changing, maybe the most important thing is not finding the answer, but continuing to ask the question. For centuries we've thought of the world in a certain way. We've imagined the universe as a vast collection of tiny solid particles, atoms, electrons, protons, each one a building block, a little piece of the puzzle. This way of thinking has served us well. It helped us understand chemistry, build technology, and explore the far reaches of space. But what if this view is only part of the story? What if, beneath the surface, the particles we've come to know and trust aren't the final answer, but just a stepping stone towards something much deeper, more fundamental? This is where string theory begins to change the game. It turns out that the particles we've been so focused on, those tiny, seemingly indivisible bits of matter, might not be the true foundation of the universe at all. Instead, according to string theory, those particles are just the result of vibrations in something much smaller, one-dimensional strings. Imagine, if you will, that instead of particles being little balls, they are tiny loops or segments of string, vibrating in different patterns. Each vibration corresponds to a different particle, a different force, a different aspect of reality itself. It's a shift in perspective that feels almost impossible at first. After all, particles have been the bedrock of our understanding for so long. How could something as intangible as a vibrating string replace them? But that's exactly what string theory suggests. What we've been calling particles are merely the manifestation of these fundamental strings in motion. When a string vibrates one way, it shows up as an electron. When it vibrates another way, it becomes a photon, the particle of light. And when it vibrates in a different way still, it might create a graviton, the elusive particle that carries gravity. This doesn't just change how we think about particles, it changes how we think about everything. Take the electron, for example. We've always pictured it as a point-like particle, small, indivisible, and fundamental. But in string theory, the electron is not a point at all. It's a string, vibrating in a specific way that makes it behave like an electron. The same goes for other particles like quarks and neutrinos. Each one is simply a different vibration of a string, and the properties of that particle, its charge, mass, and spin, are determined by how the string vibrates. This idea turns everything we know about particle physics upside down, suggesting that at the deepest level, the universe isn't made of separate solid objects at all. It's made of strings, pulsing and vibrating in an unseen dance. But it's not just particles that are affected by this new perspective. String theory also offers a way to unify the forces of nature. For decades, physicists have been trying to reconcile the two main pillars of modern physics, quantum mechanics, which describes the behavior of the very small, and general relativity, which explains gravity and the structure of space-time on a large scale. These two theories have always been at odds, unable to coexist in a single framework. Quantum mechanics works brilliantly for atoms and particles, while general relativity excels at explaining the large-scale structure of the cosmos, planets, stars, galaxies, and the curvature of space-time. But when you try to apply both theories to things like black holes or the beginning of the universe, things fall apart. The equations get messy, and the predictions become nonsensical. What string theory offers is a potential solution. Because strings can vibrate in so many different ways, they can give rise to all the forces we observe in the universe: gravity, electromagnetism, and the strong and weak nuclear forces. And because the equations of string theory allow for the existence of gravitons, it could finally provide a quantum description of gravity, something that has eluded scientists for decades. In this way, string theory doesn't just shift our perspective on particles, it shifts our perspective on the very nature of reality itself. The universe, according to string theory, isn't just a collection of individual particles and forces. It's a vast, interconnected web of vibrations, all intertwined, each string influencing and being influenced by others. Everything we see and feel, light, matter, gravity, is the result of these strings vibrating in harmony. Now, you might be wondering, how can we even begin to test this idea? After all, strings are unimaginably small, far smaller than the particles we currently study with our most powerful microscopes. In fact, they're so small that they're beyond the reach of any direct experiment we could conceive. But here's the thing. String theory is not just about the strings themselves, it's about the implications of their vibrations. For example, string theory suggests that the way the universe is structured, its dimensions, its forces, even the constants of nature, could be the result of the way strings vibrate. And while we can't directly observe strings, we can look for indirect evidence of their existence by studying the behavior of particles and forces. One of the key predictions of string theory is the existence of extra dimensions beyond the three we're familiar with. According to string theory, the universe might have 10 or even 11 dimensions, but the extra ones are so tightly curled up that we can't perceive them. These extra dimensions could help explain some of the mysteries of physics, such as why gravity is so much weaker than the other forces, or why certain particles behave the way they do. If string theory is correct, these extra dimensions could be hidden right in front of us, folded into the very fabric of space and time, waiting for us to discover them. And then there's the concept of the multiverse, which string theory also predicts. If the universe is made up of vibrating strings, and those strings can vibrate in different ways, then it stands to reason that there could be multiple universes, each one with its own set of physical laws and constants. In some universes, the laws of physics might be radically different from our own. In others, the universe might be almost identical to ours, with just a few small differences. The multiverse is still a speculative idea, but it's one that arises naturally from string theory, and it offers a whole new way of thinking about the cosmos. So, in a sense, string theory doesn't just change the way we view particles, it changes the way we view the entire universe. Instead of thinking of the universe as a collection of separate objects and forces, string theory asks us to think of it as a single, interconnected whole, a vast symphony of vibrations, each note playing its part in the grand composition of reality. It's a radical shift in perspective, and one that might take years, even centuries, to fully understand. But what makes string theory so compelling is not just its elegance or its potential to unify physics, it's the way it invites us to see the universe with fresh eyes, to think of it as something more than just a collection of objects, but as a living, breathing, vibrating entity, constantly shifting and changing, resonating with the rhythms of existence. And perhaps that's the most beautiful thing about string theory. It doesn't just offer answers. It opens up new questions, new possibilities, new ways of seeing the universe. The more we look, the more we realize how much we don't yet understand. And in that uncertainty, there's room for wonder, for discovery, and for the thrill of the unknown. Have you ever sat in complete silence just listening? Not to the hum of machines, the creak of floorboards, or the distant murmur of traffic, but to a deeper silence, a stillness so profound that it almost feels like you can hear the space around you. It's in these quiet moments that you might begin to notice something strange, something that defies the silence. It's the subtle, almost imperceptible hum of the world, a sound not created by anything we can see, but one that seems to be woven into the very fabric of existence. This hum, this vibration, isn't just metaphorical. In string theory, vibration is the key to understanding how the universe works at its deepest level. The very nature of reality, it seems, is one of constant motion, not the kind of motion we can observe with our eyes. No, this motion is far smaller, far more intricate. It happens on a scale so tiny, so beyond our perception, that it feels almost impossible to grasp. But in this tiny, invisible world of vibrations, everything we see, touch, and feel is created. Imagine, for a moment, that the universe is like a giant musical instrument. The strings of this instrument are not the guitar strings you can strum, or the piano strings you can pluck, but the tiniest, most delicate vibrations in the deepest corners of space. According to string theory, these strings are the fundamental building blocks of reality. Instead of particles whizzing around in empty space, it's these vibrating strings that create everything we know. Just like the strings of a violin or a cello, these cosmic strings vibrate at different frequencies, and depending on how they vibrate, they manifest as different particles. Some vibrations create electrons, the tiny particles that carry electricity. Others create quarks, the building blocks of protons and neutrons. And still others might give rise to the mysterious particles that carry the forces of nature, like photons for light and gravitons for gravity. Each vibration corresponds to a different aspect of the universe. It's as if the universe is playing a song, with each note corresponding to a different particle, each vibration creating a different part of the cosmic melody. But here's the thing, the music of the universe isn't something we can hear, not in the way we hear sound. Sound needs air or water, or some kind of medium to carry it. But these vibrations, these strings, exist in a space so small and so fundamental that they don't make sound waves the way we understand them. Instead, they create ripples in the very fabric of space-time. It's a kind of music that doesn't need air to travel. It's the pulse of the universe itself, vibrating through dimensions beyond our senses. This idea of vibration as the basis of everything is not just a poetic thought. It's a scientific proposal grounded in the mathematics of string theory. When scientists began to study the equations that describe the interactions between particles, they noticed something remarkable. The equation suggested that the particles weren't point-like objects, as had been assumed. Instead, they were more like little loops or strings vibrating at different frequencies. And these vibrations weren't just an interesting mathematical curiosity. They could explain the properties of particles, how they interacted with one another, how they had mass, how they carried force. Everything we know about the particles in the universe could be understood as the result of their vibrations. It's an elegant idea, isn't it? To think that the entire universe, with all its complexity and diversity, could be reduced to something as simple as a vibration. And yet, this idea has profound implications. If everything in the universe is just the result of different vibrations, then that means the universe itself is a vast interconnected symphony. Everything is linked, each note resonating with the others, creating the fabric of reality itself. Of course, this raises more questions than it answers. If everything is vibration, then what is it that's vibrating? What is the medium that carries these vibrations? And how do we know that these vibrations are real and not just an abstract concept we've invented to explain the world? The answers to these questions aren't easy to find, and string theory itself is still a work in progress. We don't yet have the experimental evidence to prove that strings exist, let alone understand the full extent of their role in the universe. But the beauty of string theory is that it opens up new ways of thinking about the world. It suggests that the universe isn't a collection of separate objects or particles, but a dynamic, interconnected whole, a cosmic orchestra playing a song we can't quite hear but are a part of nonetheless. And what's more, the idea of vibration in string theory isn't just limited to the tiny strings themselves. It extends to the very fabric of space-time. According to string theory, space and time aren't fixed, rigid entities. Instead, they are like the strings themselves, flexible, malleable, and subject to vibration. Space-time can stretch, warp, and vibrate just like a string. And just as the vibrations of strings create particles, the vibrations of space-time can create the very structure of the universe itself. This concept of vibrating space-time brings us to one of the most fascinating aspects of string theory, the idea that the universe has more than the three dimensions of space and one of time that we experience in our daily lives. String theory suggests that there may be additional dimensions, curled up tightly and hidden from view. These extra dimensions could be responsible for the forces and particles we observe, as well as the very structure of space-time itself. It's as if the universe has many layers, each one vibrating at its own frequency, and it's the interplay of these vibrations that creates the reality we know. And here's where it gets truly mind-bending. If vibration is at the heart of everything, then the universe may not be as solid and unchanging as it seems. The very fabric of space-time could be constantly shifting, rippling and vibrating in ways we can't yet perceive. And just like the strings of an instrument, these vibrations could give rise to all the forces and particles in the universe, shaping the reality we experience. So, when we look at the world around us, we're not just seeing solid objects or rigid structures. We're seeing the result of vibrations that stretch across dimensions we can't directly observe, but that are no less real for it. The music of the tiny, as it were, is playing all around us, creating the very fabric of reality. The beauty of this idea lies in its simplicity and its depth. In a universe where everything is connected by vibrations, we're all, in a sense, part of the same cosmic symphony. We may not be able to hear the music with our ears, but we can feel it in the way the universe behaves, in the way particles interact, and in the way space-time itself stretches and bends. Everything is part of the same rhythm, vibrating in harmony, creating the universe we know. So the next time you pause and listen to the world around you, try to hear the hidden music beneath the noise. The hum of existence is always there, playing its own song, whether we're aware of it or not. And if string theory is right, we might just be hearing the echo of something much deeper, a vibration that runs through the entire universe, shaping the very nature of reality itself. What if everything you've ever known, everything you've ever seen, heard or touched wasn't made of solid stuff at all? What if, beneath the surface of reality, what you consider to be solid matter is merely an intricate pattern, a vibration of energy, a ripple in a far deeper space? This is the grand suggestion of string theory, that the universe, at its most fundamental level, is not made of particles, but of tiny vibrating strings. Each of these strings, vibrating at different frequencies, gives rise to the particles that form everything we know: the stars, the planets, the atoms, and yes, even us. Now, this idea might sound like science fiction, but the more scientists have explored the possibilities of string theory, the more it begins to make sense. The beauty of string theory lies in its ability to unify the disparate pieces of our understanding of the universe into a single, elegant framework. For centuries, physicists have tried to reconcile the two great pillars of modern physics: quantum mechanics, which explains the behavior of the very small, and general relativity, which explains gravity and the large-scale structure of the universe. But these two theories have never quite worked together. Quantum mechanics has been incredibly successful at describing the world of particles and forces on the smallest scales. It explains why electrons orbit atoms in specific shells, why light behaves as both a wave and a particle, and even why particles can be in two places at once. But when you try to use quantum mechanics to understand gravity, the force that governs the movement of planets, stars, and galaxies, things get messy. The equations break down, and the predictions become nonsensical. On the other hand, general relativity has been incredibly successful at explaining the behavior of gravity. It describes how mass and energy warp space-time itself, creating the force we feel as gravity. It's the theory that explains why planets orbit stars, why light bends around massive objects, and even why black holes exist. But when it comes to describing the smallest particles, general relativity falters. It doesn't have a way of incorporating quantum mechanics into its framework. This is where string theory steps in. By replacing point-like particles with tiny, one-dimensional strings, string theory offers a way to bring quantum mechanics and general relativity together. In string theory, the very fabric of space-time is made of vibrating strings, each one oscillating at a different frequency. These vibrations give rise to the particles that make up matter, as well as the forces that govern their interactions. But string theory doesn't just unify the forces of nature, it also offers a way to explain some of the deepest mysteries of the universe. For example, one of the great puzzles of modern physics is the question of why gravity is so much weaker than the other forces. Electromagnetism, the force that governs electric charges, is vastly stronger than gravity. Yet, when we look at the universe, gravity seems to be the weakest force by far. String theory offers a potential explanation for this. According to string theory, there are more dimensions to the universe than the 3 we experience in everyday life. In addition to the familiar dimensions of length, width, and height, string theory suggests that there are additional, hidden dimensions that we can't directly observe. These extra dimensions could explain why gravity is so weak. In some versions of string theory, gravity is not confined to the 3 familiar dimensions, but instead spreads out across all the extra dimensions. This could make it appear weaker in our familiar 3-dimensional space, while still being an essential force in the overall structure of the universe. This idea of hidden dimensions is one of the most fascinating aspects of string theory. If string theory is correct, then there are dimensions of space that we can't see or touch. These dimensions are thought to be tightly curled up, smaller than the smallest particle. They are woven into the fabric of space-time, hidden from our perception, yet influencing everything in the universe. These hidden dimensions could also help explain other mysteries, such as why the constants of nature seem to have just the right values to support life. In fact, string theory suggests that there may be an infinite number of possible universes, each with its own set of physical laws. This idea is called the multiverse, and it arises naturally from the mathematics of string theory. If the universe is made up of vibrating strings, then it stands to reason that the different ways those strings can vibrate might lead to different sets of physical laws. In some universes, the strength of gravity might be much stronger than it is in ours. In others, the laws of physics might be completely different. The multiverse is still a speculative idea, but it's one that could explain why our universe seems so finely tuned for life. And then there's the concept of the fundamental forces. In string theory, all the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are the result of different vibrations of the same underlying strings. Each of these forces corresponds to a different vibrational pattern, a different note played by the strings. This idea offers a new way to think about the forces of nature. Instead of seeing them as separate independent forces, string theory suggests that they are all part of a larger interconnected whole. The universe is not a collection of isolated forces, but a unified system in which every force is related to the others through the vibrations of strings. This unification of forces is one of the most exciting aspects of string theory. For centuries, scientists have been searching for a theory of everything, a single framework that can explain all the forces and particles in the universe. String theory, with its ability to unite gravity, electromagnetism, and the nuclear forces under a single umbrella, is the closest we've come to that elusive theory. And yet, despite its elegance and its potential, string theory is still not proven. The math is complex, and there is no direct experimental evidence to confirm the existence of strings. String theory operates at a level so deep and so small that it's difficult, if not impossible, to test directly with current technology. But what makes string theory so compelling is that it doesn't just explain the forces of nature, it provides a new way of looking at the universe. It suggests that everything we know, everything we experience, is the result of something much deeper, something far more fundamental than the particles we've been studying for centuries. What string theory offers is a new perspective on the universe. It asks us to look beyond the particles and forces that we can see and touch, and consider the possibility that the universe is not a collection of solid objects at all, but a web of interconnected vibrations. The very fabric of reality, it suggests, is made of strings that vibrate and give rise to the universe we see. It's a profound shift in our understanding of reality, and one that could change the course of physics forever. In the end, string theory may or may not be the final answer. We may never be able to directly observe the strings themselves, but the beauty of the theory lies in the way it unites our understanding of the universe, offering a possible explanation for everything we see. In a sense, string theory is an invitation to look deeper, to explore the hidden patterns of the universe, and to imagine a reality that's more connected, more harmonious than we've ever thought possible. Have you ever wondered what it would be like to live in a world with more than the 3 dimensions of space that we experience every day? Imagine for a moment that the world around you didn't just have width, height, and depth. What if, hidden from our view, there were other dimensions we can't see, touch, or even comprehend, but that are there, influencing everything? These hidden dimensions could hold the key to unlocking some of the most profound mysteries of the universe, and according to string theory, they just might. String theory suggests that our universe is not confined to just the familiar 3 dimensions of space. Instead, it proposes that there are as many as 11 dimensions, some of which are so small and tightly curled up that we don't even notice them. Think of them like secret hallways hidden within the very fabric of space and time, so tiny that even the most powerful microscopes can't detect them. These extra dimensions are a crucial part of string theory because they allow for the existence of the vibrations that create all the particles and forces we see around us. The idea of 11 dimensions might sound bewildering at first. How could something so invisible, so far beyond our senses, affect the world we see? But when you stop and think about it, it starts to make a certain kind of sense. After all, our senses are limited. We can't see ultraviolet light, hear sounds beyond a certain frequency, or feel the tiniest particles vibrating in space. Just because something is beyond our perception doesn't mean it doesn't exist. In fact, most of the things that shape our lives, like gravity or electromagnetism, are forces we can't directly see, but we can certainly observe their effects. According to string theory, these extra dimensions are responsible for much of the complexity of the universe. They provide the space in which strings can vibrate, and in doing so, they give rise to the particles and forces that govern everything. Each extra dimension adds another layer of possibility to the universe, creating more room for the strings to vibrate in different ways. In some versions of string theory, these extra dimensions are thought to be compactified, folded up so tightly that they're beyond our ability to detect. But they're still there, hidden from view, waiting for us to uncover their secrets. But why 11 dimensions? Why not just 2 or 10? The answer, it turns out, lies in the mathematics of string theory. When physicists first began exploring string theory, they found that the equations worked best when there were 10 dimensions, 9 of space and 1 of time. But as they refined the theory and began to take into account the influence of gravity, they discovered that 11 dimensions were necessary to fully explain the interactions of the forces in the universe. It's a bit like trying to fit a puzzle together. If you're missing a piece, the puzzle just doesn't work. 11 dimensions seem to be the right number to make the puzzle of string theory fit together. Now, you might be asking, if these dimensions are so tiny and so curled up, why don't we notice them? The answer is that they're hidden from our perception because they're incredibly small, far smaller than anything we can detect with current technology. These extra dimensions are thought to be compactified, meaning that they're folded up so tightly that they exist only on the tinier scales, far beyond the reach of our senses or our instruments. They're like the tiny creases in a piece of paper that you can't see unless you unfold it, or like a book with extra pages that are hidden in the spine. They're there, but they're not something we can easily access or observe. And yet, even though we can't see these extra dimensions, they might still influence the way we experience the universe. For example, the strength of gravity could be explained by how the extra dimensions are structured. In some versions of string theory, gravity is not confined to the 3 familiar dimensions of space, but instead spreads out across all the extra dimensions. This could help explain why gravity is so much weaker than the other forces. If gravity is diluted across more dimensions, it would appear much weaker in the 3 dimensions we can observe, even though it's actually just as strong as the other forces on a higher level. This idea of hidden dimensions also opens up a fascinating possibility, that there might be other universes, each with its own set of dimensions and physical laws. In the multiverse scenario, each universe could have a different number of dimensions, or the dimensions could be arranged in completely different ways. Some universes might have only a few dimensions, while others might have many more, and in each of these universes the strings could vibrate differently, creating entirely different sets of particles and forces. It's a mind-boggling thought, but it's one that arises naturally from the mathematics of string theory. But let's take a moment to pause and reflect on what this all means. If string theory is right, and there really are 11 dimensions hidden beneath the surface of reality, then the universe is far more complex and beautiful than we've ever imagined. What we see, feel, and touch might only be the surface of a far deeper, more intricate reality. The extra dimensions provide the stage on which the strings vibrate, creating the particles and forces that make up our world. They are the hidden symphony of the universe, the silent orchestra that plays the music of existence. And just as a musician can play many different instruments, creating a rich and varied sound, so too can the strings of the universe vibrate in many different ways, creating a vast array of particles and forces. The 11 dimensions of string theory offer the potential for an almost infinite variety of combinations, each one giving rise to a different version of the universe. This could explain why our universe has the particular properties it does, why the forces of nature are just the right strength, why atoms form in the way they do, and why life exists in the way it does. It's as if the universe is a vast cosmic symphony, with each string playing its part in the grand composition of reality. But for all its beauty, string theory remains a work in progress. The extra dimensions, while mathematically elegant, are still beyond our reach. We can't directly observe them, and we don't yet have the technology to probe them. Yet the very fact that these dimensions are suggested by the theory is a testament to the power of human imagination and curiosity. String theory is asking us to stretch our minds, to think beyond the limitations of our senses, and to imagine a reality that's far more complex and interconnected than we've ever dreamed. In the end, the idea of 11 dimensions is both humbling and awe-inspiring. It reminds us that there is so much more to the universe than we can see. The extra dimensions are like hidden strings, vibrating just out of sight, shaping the reality we experience. They are the silent symphony that plays beneath the surface of the world, and perhaps, as we continue to explore the mysteries of string theory, we'll begin to hear more of the music. Imagine for a moment that you're listening to a piece of music. You can hear the instruments, the melody, the rhythm, but there's something that's not quite right. The notes don't line up perfectly, the harmony feels incomplete, and the music, while beautiful, feels unfinished. That's the state of string theory today. It's an elegant, breathtakingly complex theory, and yet it remains a work in progress, unfinished, unproven, and uncertain. But despite its incomplete status, it offers a glimpse of something much greater, something that might one day tie together the entire fabric of the universe. The promise of string theory lies in its potential to unify all the forces of nature into a single, cohesive framework. For decades, scientists have sought a theory of everything, a way to explain gravity, electromagnetism, and the nuclear forces under one roof. String theory offers just that, a way to describe all of these forces as different manifestations of one underlying principle. The theory suggests that the universe is not made of solid particles, as we once thought, but of tiny vibrating strings. These strings, vibrating in different ways, give rise to the particles we observe and the forces that govern their interactions. It's an elegant solution to some of the deepest puzzles of physics. But despite its elegance, string theory has yet to be proven. And that's not for lack of trying. The problem lies in the fact that string theory operates at a scale far smaller than anything we can currently observe. The strings themselves are thought to be incredibly tiny, so small that they are far beyond the reach of our most powerful microscopes. They exist on a scale that is so minuscule, it's difficult, if not impossible, to detect them directly. And without direct evidence of the strings themselves, it's hard to say for certain that string theory is correct. This is a central challenge in physics. How do you prove a theory that deals with things that are so small, so hidden from view, that we can't even begin to measure them? Scientists have proposed various ways of testing string theory indirectly, but so far none of them have provided definitive evidence. For example, one possible test of string theory involves looking for the presence of extra dimensions. String theory predicts that there are more than the 3 dimensions of space that we experience in our daily lives. But these extra dimensions are thought to be compactified, curled up so tightly that they're invisible to us. The hope is that, in the future, we might be able to detect the effects of these extra dimensions, perhaps through experiments involving high-energy particles or cosmological observations. Another way to test string theory is through the study of black holes. String theory predicts that the behavior of black holes should be different from what we currently understand, and studying the details of black holes could offer valuable clues about the nature of strings. But again, this is a complex and challenging task. Black holes are difficult to study directly, and the theoretical models that string theory provides are still being developed and refined. And then there's the problem of the multiverse. One of the predictions of string theory is that there may be multiple universes, each with its own set of physical laws and constants. This idea, known as the multiverse, is a fascinating one, but it's also difficult to test. If there are other universes beyond our own, how do we observe them? How do we gather evidence for something that's, by definition, beyond our reach? Some scientists argue that the multiverse is a purely philosophical concept, while others believe that it could one day be testable. But for now, the idea remains speculative, and without concrete evidence, string theory remains unfinished. This is not to say that string theory is without merit. In fact, it's one of the most beautiful and promising frameworks in modern physics. Its ability to unify the forces of nature, its potential to explain the deepest mysteries of the universe, and its elegance in the face of complexity are all compelling reasons why string theory continues to be studied. But for all its promise, it's still a theory without proof, a piece of music that is unfinished, awaiting its final notes. It's important to understand that this doesn't mean string theory is useless or irrelevant. Far from it. String theory has already led to important insights in mathematics and physics. It has inspired new ways of thinking about the nature of space, time, and gravity. It has provided new tools and frameworks for understanding quantum mechanics and general relativity. And it has opened up new areas of research that could one day lead to breakthroughs in our understanding of the universe. But the truth is, we're still a long way from proving string theory. It's a theory that exists mostly in the realm of abstract mathematics and theoretical physics, and while it offers a glimpse of a unified framework for understanding the universe, we don't yet have the experimental evidence to confirm it. This leaves us in a kind of scientific limbo, aware of the beauty and potential of the theory, but unable to say for sure whether it's the right answer. The unfinished nature of string theory is a reminder of the complexity of the universe and of the limits of our current understanding. The questions it raises are profound, and the answers may be elusive, but that doesn't make the search for those answers any less important. String theory, despite its lack of proof, represents the cutting edge of our quest to understand the fundamental nature of reality, and as we continue to explore the depths of the cosmos, we might one day find the evidence that proves string theory right, or perhaps we might discover something even more surprising. For now, we remain in the dark, listening to the unfinished score of the universe, waiting for the final notes to be played. And even if those notes remain just out of reach, there's something beautiful about the journey. the search for the answers, the questions that drive us forward, and the music of the universe that we're only beginning to hear. As we journey further into the heart of string theory, we begin to encounter even stranger and more fascinating ideas. We've already touched on the concept of tiny vibrating strings, but what happens when we zoom out, or when we consider how those strings interact with one another and with the very fabric of space-time itself? It's in this territory that we start to encounter some of the most mind-bending concepts of string theory: loops, brains, and a whole range of other strange instruments that form the backdrop to the universe's most fundamental workings. Let's start with loops, a concept that first emerged when scientists began to think more deeply about how strings could move and interact in the universe. A loop, as the name suggests, is a string that doesn't just vibrate in one direction, but instead forms a closed circular shape. Imagine a tiny rubber band, flexible, elastic, and capable of stretching and bending in ways that can't be observed in the everyday world. These loops can move freely through space-time, twisting and turning in response to forces around them, and as they do, they create the building blocks of reality. At first glance, loops might seem like just another part of the string theory puzzle, but they turn out to be incredibly important. They offer a new way of thinking about particles and forces, and they help to explain some of the most perplexing aspects of quantum physics. For instance, the behavior of loops in string theory can help us understand how particles might behave in extreme environments, like inside black holes, or how gravity might work on the smaller scales. Loops don't just vibrate, they can also wrap around themselves, creating closed paths that act like tiny quantum circuits. These closed loops give rise to a range of different forces, including gravity itself, suggesting that gravity may not be as separate from the other forces as we once thought. Instead, it could be part of a larger network of interwoven forces, all emerging from the same fundamental principle. But loops are just the beginning. As string theory evolved, scientists began to consider more complex objects called brains. A brain, short for membrane, is a multi-dimensional object that extends beyond the familiar 3 dimensions of space. Just as strings are one-dimensional objects, brains are higher dimensional structures, and they can exist in various shapes and forms. In some versions of string theory, brains are fundamental objects that make up the very structure of space-time itself. Instead of thinking of the universe as a collection of points, particles, and strings, Brun suggests that the universe is made up of vast, multi-dimensional sheets that stretch and vibrate in ways we can't directly perceive. One of the most intriguing aspects of brains is their relationship to the extra dimensions predicted by string theory. While strings exist in the familiar 3-dimensional world, brains can exist in these hidden, extra dimensions. In some versions of string theory, our entire universe might exist on a brain, floating in a higher dimensional space. This idea is known as the brain world hypothesis, and it has profound implications for our understanding of the universe. If we live on a brain, then everything we see, the stars, the planets, even the forces of nature, might be confined to that brain, while the higher dimensional space that contains the brain remains hidden from us. But there's more to brains than just being the stage on which the universe plays out. Brains themselves can have interesting properties. For example, they can carry energy, and their movements can create the forces that govern the universe. This is where things get truly mind-bending. Imagine a massive brain, stretching out across multiple dimensions and interacting with smaller brains, like the strings that vibrate within it. When these brains interact, they can create ripples in space-time, much like the ripples you might see when 2 stones are thrown into a pond. These ripples could, in theory, give rise to the particles and forces that shape our universe. But brains also raise a number of intriguing questions. For one, if we live on a brain, what happens to the space outside of it? Could there be other brains floating in higher dimensional space, each with its own set of physical laws? The idea of a multiverse, with multiple brains each containing a separate universe, becomes a natural consequence of this thinking. if brains are the fundamental building blocks of reality, then it's possible that each brain could be its own universe, with its own set of physical constants and forces. In this way, string theory offers a potential framework for understanding the multiverse, a concept that could explain the apparent fine-tuning of our universe and the nature of reality itself. The implications of brains and loops are profound. They challenge our understanding of space, time, and the very structure of the universe. Instead of imagining a universe made of separate particles and forces, string theory invites us to think of a universe made of interwoven dimensions, loops, and brains, all vibrating in harmony to create the reality we experience. It's a universe that's far more complex, far more connected than we ever thought possible. And yet, despite the beauty and elegance of these ideas, there's still a great deal we don't understand. String theory, with its loops and brains, is a theory in development. The math is intricate and powerful, but the experimental evidence is still elusive. As of now, we don't have the technology to directly observe the loops or brains that string theory predicts, and so much of the theory remains speculative. For all the excitement that string theory generates, it's still very much an unfinished symphony, one that's waiting for the final notes to be played. But that's what makes string theory so exciting. It's not just a theory that explains the particles and forces we already know. It's a theory that opens up new realms of possibility. It challenges our understanding of the universe, and it pushes the boundaries of what we think is possible. It suggests that the universe is not just a collection of particles and forces, but a dynamic, ever-evolving web of dimensions, strings, loops, and brains, all vibrating in unison. And so, as we continue to explore the mysteries of the universe, we find ourselves listening to an unfinished score, one that hints at the deeper symmetries of the cosmos. The music may not be fully understood yet, but it's there, waiting to be discovered. As we uncover more about the hidden world of strings and brains, we move closer to a deeper understanding of the universe, one that could change the way we see everything. Beneath the everyday world that we can see, touch, and measure, there lies another realm, a hidden world so strange and elusive that it often feels more like a dream than reality. It's the world of quantum mechanics, where the rules of physics we take for granted, like cause and effect or the certainty of where something is at any given moment, seem to vanish, replaced by probabilities and uncertainties. In the quantum world, particles don't behave like solid objects. They exist in a state of possibility, a kind of quantum dance that can only be understood through the language of probability. This dance is at the heart of string theory. At its core, string theory proposes that the universe is made up not of rigid, unchanging particles, but of tiny, vibrating strings. These strings vibrate in different ways, creating the particles and forces we observe in our everyday lives. But just like the particles they create, these strings don't follow the predictable, deterministic laws that govern the world we know. Instead, they exist in a state of constant flux, vibrating and interacting with each other in ways that are governed by the strange rules of quantum mechanics. At the quantum level, particles are not fixed, discrete objects. They exist as probabilities spread out across space and time. A particle doesn't have a definite position or momentum until we observe it. Until then, it exists as a kind of fuzzy cloud of possibilities, a wave of potential outcomes. This is called wave-particle duality, the idea that particles can behave both like waves and like particles depending on how they're measured. It's a concept that's at the heart of quantum mechanics, and one that has baffled scientists for nearly a century. The strange thing about this quantum dance is that it doesn't just apply to individual particles. It applies to the very fabric of space-time itself. According to string theory, space-time is not a smooth, unchanging stage on which the dance of particles occurs. Instead, space-time is itself made of vibrating strings, each of them interacting and influencing the others. The entire universe, in this view, is a vast interconnected web of strings, all vibrating in harmony to create the reality we experience. This idea of space-time as a dynamic, vibrating medium leads us to one of the most mind-bending aspects of string theory: the idea that gravity, the force that governs the motion of planets, stars, and galaxies, is not a separate force at all. Instead, it's a natural consequence of the vibrations of strings. Gravity in string theory is carried by particles called gravitons, which are the result of specific vibrations in the strings. Just as light is carried by photons, gravity is carried by gravitons, and both are part of the same cosmic dance, orchestrated by the vibrating strings of the universe. But the quantum dance beneath reality doesn't stop there. One of the most fascinating aspects of quantum mechanics is the phenomenon of entanglement. In a quantum system, particles can become entangled, meaning that their properties become linked, even if they are separated by vast distances. When one particle is measured, the state of the other particle is instantly determined, no matter how far apart they are. This seems to defy the laws of relativity, which state that information cannot travel faster than the speed of light. Yet, in the quantum world, entangled particles seem to communicate with each other instantaneously. Entanglement is one of the key features of quantum mechanics that makes the quantum dance so difficult to understand. It suggests that at the deepest levels of reality, everything is connected, even across vast distances. It's as if the universe itself is a kind of cosmic symphony, with every particle, every string, playing its part in the same grand melody. And just as a violinist can play a note that resonates with the entire orchestra, so too can the vibrations of one string influence the vibrations of another, no matter how far apart they are. This interconnectedness, this deep entanglement of everything in the universe, is one of the most profound and mysterious aspects of quantum mechanics. But as fascinating as these ideas are, they don't come without their challenges. The quantum dance is not an easy one to follow. It's a dance that takes place in a world where the rules are vastly different from those we're used to. Particles exist in multiple states at once, and their behavior is governed by probabilities rather than certainties. Even the concept of time itself becomes blurry at the quantum level, with particles existing in a kind of timeless state until they're measured. It's a world that feels counterintuitive and strange, and one that we can only glimpse through the veil of our limited senses. Yet, despite its strangeness, the quantum dance is an essential part of the universe. Without it, we wouldn't have atoms, molecules, or the forces that govern the universe. Without the dance of quantum particles, the universe as we know it simply wouldn't exist. It's the unseen rhythm of existence, the pulse that drives the cosmos forward. And string theory, in its elegant complexity, gives us a way to understand that rhythm. By positing that everything in the universe, from the smallest particles to the vast stretches of space-time, is made up of vibrating strings, string theory offers a unified framework that ties together the quantum dance with the larger classical forces of the universe. It suggests that the strange, unpredictable behavior of quantum particles is not a random occurrence, but part of a larger, deeper pattern. A cosmic choreography that has been unfolding since the beginning of time. The beauty of string theory lies in its ability to offer a coherent explanation for the mysterious and often bewildering phenomena of the quantum world. It connects the dots between the smallest scales of reality and the largest, between the realm of particles and the vastness of space. It shows us that the universe is not made of solid, unchanging matter, but of dynamic, interconnected strings, each vibrating in its own unique way. It's a universe that's alive with movement, a place where the fundamental laws of nature are not fixed and unyielding, but flexible and fluid, shaped by the dance of the strings. So the next time you think about the world around you, take a moment to imagine the quantum dance beneath it all. It's a dance that's always happening, even when we're not aware of it, a rhythm that shapes the very fabric of reality. And if string theory is right, it's a dance that stretches across the cosmos, from the tiniest particles to the vastest galaxies, all vibrating in unison, creating the universe we live in. Gravity. It's the force that holds us to the ground, that keeps the planets in orbit around the sun, and that shapes the very structure of the cosmos. It's so familiar to us that we hardly ever think about it, until we drop something, or feel the weight of an object, or look up at the stars and wonder why they don't simply drift away. Gravity, we're told, is a force of attraction, an invisible pull that pulls us toward the centre of the Earth and keeps the moon tethered to our planet. But what if, just beneath the surface of this force, there's something far more profound at work? What if gravity is not just a simple pull, but a deep, cosmic vibration, a resonance that echoes through space-time itself? This idea, which seems almost poetic, is at the heart of string theory. String theory suggests that gravity is not a separate force, as it has often been treated in physics, but rather it's a manifestation of the vibrations of tiny strings. Just as strings vibrating in different patterns can give rise to particles like electrons and photons, so too can the vibrations of strings give rise to gravitons, the particles that carry the force of gravity. In this view, gravity is not a mysterious, invisible force acting at a distance. It is the result of specific vibrations of strings in the quantum world, a force that is woven into the very fabric of space and time. To understand this idea, we have to go back to the foundations of physics, to the work of Einstein and his theory of general relativity. In the early 20th century, Einstein revolutionized our understanding of gravity with his theory of general relativity. According to general relativity, gravity is not simply a force pulling objects together. Instead, gravity is a warping of space-time itself. Massive objects like planets and stars create a dent in the fabric of space-time, and this curvature causes other objects to move in predictable ways. In essence, objects are following the curves of space-time, and this is what we experience as gravity. But while general relativity was a brilliant theory, it has some shortcomings. For one, it doesn't incorporate quantum mechanics, the theory that describes the behavior of the very small, like atoms and particles. In the quantum world, things are governed by probabilities and uncertainties, while in the classical world of relativity, things behave in a much more predictable and deterministic way. And while general relativity has been incredibly successful in explaining the behavior of large objects like planets, black holes and galaxies, it doesn't provide a complete picture of gravity at the smallest scales where quantum mechanics reigns. This is where string theory comes in. In string theory, gravity is not something separate or distinct. It is instead a product of the vibrations of tiny strings which interact with the other forces of nature. Just as the electromagnetic force is carried by photons, gravity is carried by gravitons. And just as photons interact with the electromagnetic field, gravitons interact with the fabric of space-time itself. They are the tiny messengers of gravity, carrying its force from one point to another, just as sound waves carry the vibrations of a musical note through the air. But what makes gravity so unique is that, unlike the other forces, it is incredibly weak. Electromagnetism, for example, is far stronger than gravity, and the strong and weak nuclear forces are even more powerful. So why is gravity so much weaker? In string theory, the answer lies in the hidden dimensions predicted by the theory. String theory suggests that our universe has more than the familiar 3 dimensions of space and 1 of time. Instead, there may be as many as 11 dimensions, some of which are curled up so tightly that we can't directly perceive them. The idea is that gravity, unlike the other forces, is not confined to the 3 familiar dimensions of space. Instead, it spreads out across all of the extra dimensions predicted by string theory. In this view, gravity appears weak because it is diluted across these extra dimensions, while the other forces are confined to our familiar 3-dimensional world. This could explain why gravity is so much weaker than the other forces. It's simply not concentrated in the same way. But even though gravity might seem weaker, it has a secret power. In the quantum world, gravity is still a force to be reckoned with, and in certain circumstances like near black holes or the beginning of the universe, gravity becomes the dominant force. In fact, string theory suggests that the force of gravity could be incredibly strong at the tinier scales, and that the very fabric of space-time itself might be influenced by the vibrations of strings. This means that gravity is not just a force acting at a distance, but a deep, intrinsic part of the universe, woven into the very structure of reality. And here's where it gets even more interesting. The nature of gravity in string theory may hold the key to some of the biggest mysteries in physics, like the nature of black holes, the origins of the universe, and the relationship between quantum mechanics and general relativity. String theory suggests that the behavior of gravity on small scales could help us understand how space and time themselves behave at the quantum level. This could lead to a theory of quantum gravity, one that unites the strange probabilistic world of quantum mechanics with the smooth, curved space-time of general relativity. But there's a catch. Just as with string theory as a whole, gravity's secret voice is yet to be proven. We can't directly observe gravitons, and we don't have the technology to measure the effects of these extra dimensions that might explain gravity's weakness. We don't yet have the tools to probe the quantum nature of gravity, nor do we know exactly how to test string theory's predictions in a way that would give us conclusive evidence. And yet, string theory offers a tantalizing possibility that gravity, once thought of as a simple force of attraction, is actually a complex, multi-dimensional vibration, a resonant pulse that echoes throughout the universe, shaping the fabric of reality itself. This perspective on gravity gives us a new way of thinking about the universe. Instead of seeing gravity as a force that simply pulls things together, we begin to see it as an integral part of the cosmic symphony, a vibration that carries information, that influences the structure of space-time, that connects everything in the universe. Gravity's secret voice, it turns out, is not a quiet, passive force. It's an active player in the dance of the cosmos, shaping the very structure of reality and influencing the way particles and forces interact. So, the next time you feel the pull of gravity, when you sense the weight of your body on the earth, or watch an apple fall from a tree, take a moment to wonder, is there more to gravity than meets the eye? Is it possible that gravity, in all its mysterious power, is just a manifestation of something deeper, something that's woven into the very fabric of space-time itself? If string theory is correct, then gravity's secret voice is not only part of the universe's symphony, it's a melody that we've only just begun to understand. There are places in the universe where even light itself can't escape. Places so dense, so warped by gravity, that they bend the very fabric of space and time. These are the black holes, the cosmic enigmas that have fascinated scientists and captivated the imagination of the public for generations. Black holes are often thought of as the ultimate voids, the point where space and time break down. They are the places where reality itself seems to collapse, and all that remains is a singularity, a point of infinite density, where our understanding of physics falls apart. But what if black holes, instead of being the end of everything, were actually part of the universe's ongoing song? What if, instead of being silent, these cosmic giants were vibrating, singing their own unique notes, contributing to the grand symphony of the cosmos? This is one of the fascinating possibilities that string theory presents. According to string theory, black holes are not just gravitational traps where nothing can escape. They may also be places where the very vibrations of the strings, the building blocks of the universe, are stretched and distorted in ways that we can only begin to understand. In fact, some physicists suggest that black holes might be a kind of cosmic string instrument, resonating with the vibrations of the universe and playing a role in the structure of reality itself. To understand this, we need to take a step back and think about what makes a black hole so strange. A black hole forms when a massive star runs out of fuel and collapses under its own gravity. As the star's core contracts, it becomes so dense that its gravitational pull becomes incredibly strong. In fact, it becomes so strong that not even light can escape from it, creating a region known as the event horizon, the point of no return. Inside this boundary, all paths lead toward the singularity, where gravity is thought to become infinite, and space-time itself warps and distorts. But string theory suggests that black holes may not be as simple as they appear. Rather than being a singular point where all the mass of the star is concentrated, a black hole may actually be a multi-dimensional object. A brain, if you will. In string theory, black holes are not just points of infinite density. They may be higher dimensional objects that vibrate and interact with the strings and brains of the universe. Just as vibrating strings give rise to particles and forces, the vibrations of black holes could give rise to new forms of energy and information, potentially holding the key to some of the universe's most profound mysteries. One of the key ideas that emerges from string theory is that the information that falls into a black hole, information about particles, forces, and the structure of the universe, may not be lost forever, as once thought. Instead, this information could be encoded in the vibrations of the strings and brains that make up the black hole. This idea, known as the black hole information paradox, has been one of the most puzzling questions in physics. For decades, scientists believed that any information that fell into a black hole was lost to the universe, unable to be recovered. But string theory suggests that the information could be preserved, encoded in the very fabric of the black hole's vibrations. This idea, if proven, would have profound implications for our understanding of both black holes and the nature of reality itself. It would mean that black holes are not just cosmic prisons, but intricate vibrating structures that store information about the universe. Rather than being places where the laws of physics break down, black holes could be fundamental to the way the universe functions, playing a key role in the ongoing dance of strings and brains that creates everything we know. But how do we test this idea? How can we observe the vibrations of a black hole, let alone the information that might be encoded within them? While we don't yet have the technology to directly measure the vibrations of black holes, string theory offers some intriguing possibilities. One of the most exciting developments in recent years has been the study of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. In 2015, scientists made history by detecting the first gravitational waves from the collision of two black holes. This discovery confirmed one of the key predictions of general relativity, and it opened up a new way of studying black holes. If black holes are indeed vibrating objects, as string theory suggests, then gravitational waves could provide a way to measure these vibrations. By studying the way gravitational waves propagate through space, scientists might one day be able to learn more about the structure of black holes and the information they contain. In this way, gravitational waves could become a kind of cosmic microphone, picking up the song that black holes are singing and revealing the hidden rhythms of the universe. The idea of black holes as instruments in the cosmic orchestra doesn't stop with gravitational waves. String theory also suggests that black holes might play a role in the creation of new universes. In some models of string theory, it's proposed that when a black hole reaches the end of its life and evaporates via a process known as Hawking radiation, it might give birth to a new universe, one that emerges from the singularity of the black hole, like a seed sprouting in the fertile soil of space-time. This concept is known as the black hole cosmology, and it suggests that black holes could be gateways to new realities, connected to the fabric of the multiverse. This idea, of course, is highly speculative. We have no direct evidence that black holes create new universes, and we may never have the tools to prove it. But the possibility that black holes are not just the end of everything, but the beginning of something new is a fascinating and profound idea. It suggests that the universe itself is constantly evolving, with black holes playing a central role in its ongoing creation and transformation. The idea of black holes as cosmic instruments, resonating, vibrating, and contributing to the song of the universe, offers a new way of thinking about these mysterious objects. They are no longer just gravitational traps, but part of the larger interconnected web of strings and brains that make up the cosmos. They are places where the fundamental laws of the universe are written and rewritten, where information is encoded and preserved, and where the very nature of space-time itself is shaped and distorted. So, as you gaze up at the night sky, looking out toward the stars and wondering what lies beyond, remember this. The black holes that populate the universe are not just empty voids. They're part of the ongoing cosmic symphony, playing their own unique notes in the grand composition of reality. And perhaps, one day, when we've uncovered more about the strange music of black holes, we'll hear the song they've been singing all along, a song that could reveal the deeper secrets of the universe itself. There's a strange kind of connection in the universe, one that defies distance and time, one that seems to ignore the rules of common sense. It's called quantum entanglement, and it might be one of the most mysterious and beautiful phenomena in all of physics. At its heart, it's the idea that two particles, no matter how far apart they are, can become linked in such a way that what happens to one instantly affects the other. Einstein famously called it spooky action at a distance. And even though he was skeptical of it, decades of experiments have shown that it's real. But string theory takes this already strange idea and places it into an even grander context. If everything in the universe is made of tiny vibrating strings, then entanglement isn't just an odd quantum trick. It might be one of the fundamental features of the cosmic symphony. It could be the way the universe keeps its hidden harmony, making sure that every note resonates with every other, even across vast stretches of space. To understand how this works, imagine two strings vibrating in perfect unison. If you pluck one, the other begins to move, even if it's not physically connected to it. This isn't just an analogy. It's a way to think about how entanglement seems to behave. In quantum mechanics, particles that interact in a certain way become entangled, and once they are, their properties become forever linked. If you measure the spin of one particle, you instantly know the spin of the other, even if it's light years away. What's remarkable about this is that it doesn't seem to matter how far apart the particles are. They could be on opposite sides of the universe, and yet they would still know about each other's state. This isn't because information is travelling between them faster than light. It's because, in a sense, they were never really separate to begin with. In the quantum world, distance doesn't work the same way it does for us. Instead, entangled particles are part of the same underlying system, connected by something deeper than space itself. And if string theory is correct, that something deeper might be the strings themselves. After all, if the universe is built from tiny vibrating strings woven into the fabric of space-time, then perhaps entanglement is simply the result of these strings being connected in ways we can't see. What looks like two separate particles might just be two ends of the same vibrating thread, or two notes in the same hidden chord, forever tied together. Entanglement also leads to some startling implications about the nature of reality. For one, it challenges our idea of locality, the notion that things can only be affected by their immediate surroundings. In the world of entanglement, what happens here can influence what happens there without any signal or force travelling between them. It's as if the universe itself doesn't care about the boundaries we think of as space. And if everything is built on strings that exist in higher dimensions, then this non-locality might not be strange at all. It might simply be the natural consequence of a universe that's far more connected than it looks. This interconnectedness could even extend beyond particles. Some researchers have speculated that entanglement might be the glue that holds space-time together, the deep stitching that binds reality into a single coherent whole. In fact, there's a bold idea in theoretical physics that the very fabric of space-time might emerge from quantum entanglement. In other words, the geometry of the universe, its shape, its structure, its dimensions, could be the result of countless entangled strings vibrating in unison. weaving reality itself like a vast invisible tapestry. And if that's true, then entanglement is not just a weird quantum curiosity. It's the reason anything exists at all. It's the hidden harmony beneath the surface of the cosmos, the reason the notes of the universe play together instead of falling into chaos. Even black holes, those mysterious engines of gravity and information, may be tied to entanglement. There's an idea known as the ER-EPR conjecture, which suggests that entangled particles might be connected by microscopic wormholes, tiny tunnels through space-time. If this is correct, then the universe could be filled with hidden connections, shortcuts linking distant regions of space, all born from entanglement. In a way, it would mean that every pair of entangled particles is a tiny bridge in the unseen architecture of the cosmos, a subtle reminder that nothing in this universe is truly isolated. And this, once again, ties us back to string theory's central melody. If everything is vibration, every particle, every force, every point in space-time, then entanglement might be what happens when those vibrations overlap and lock into harmony. The universe isn't just made of individual notes, it's made of chords. And those chords don't care about distance. They resonate across the entire score of existence. So the next time you think of two particles separated by light years but still connected, try to picture it not as a bizarre quantum trick but as music. Invisible, inaudible, but real. Two notes in perfect resonance playing their part in the grand cosmic composition. And maybe, just maybe, we're entangled too, woven into this same vibrating web, humming quietly with the rest of the universe, connected in ways we're only just beginning to imagine. Time is something we live inside of so deeply and constantly that we hardly notice it. It ticks along with every second, measured by clocks, marked by the rising and setting of the sun, by the seasons that come and go. But when you step into the world of string theory, time becomes far less straightforward. It stops behaving like the steady river we imagine it to be, and starts to look more like part of the music itself, a rhythm that emerges from the vibration of the universe's strings. In our everyday experience, time feels linear. One moment follows another, and the past flows into the present, which flows into the future. But physics has been hinting for a long time that this isn't the whole story. Relativity showed us that time is not universal. It stretches and compresses depending on how fast you move or how close you are to a massive object. Two people in different places or moving at different speeds can actually experience different amounts of time passing. Time is not fixed, it's flexible. String theory takes this idea even further. In a universe built of vibrating strings, time is not something separate from the music of existence, it's part of it. The vibrations of the strings don't just create particles and forces, they also give rise to the structure of space and time itself. In this view, time isn't an independent backdrop against which the universe plays out. It's one of the notes in the grand symphony. To imagine this, think of a drum. Hit the drum, and you don't just hear a sound, you feel it. The vibration travels through the drumhead and creates both rhythm and tone. Now stretch this metaphor into the fabric of the cosmos. If strings are vibrating in hidden dimensions, their oscillations could be what generates time, much the way rhythm gives music its pulse. This way of thinking leads to a profound question. If the strings stopped vibrating, if the music of the universe went silent, would time itself stop too? Some physicists have wondered if time, as we experience it, might not be fundamental at all. It could be emergent, something that arises from deeper processes. In other words, time might not be a basic ingredient of reality. It might be something that appears when the vibrations of the universe interact in certain ways, the same way a melody emerges from individual notes. This would also help explain why time behaves so strangely at the quantum level. In the world of particles and strings, time doesn't seem to flow in a neat, orderly line. Quantum mechanics describes a realm where events don't always have a clear before and after, where particles can exist in multiple states at once, and where the usual order of time seems to blur. If time is not fundamental but instead comes from the way strings resonate, then this strange quantum timelessness starts to make sense. It isn't broken, it's just the raw, unshaped state of reality before time as we know it emerges. And this also ties into one of the biggest puzzles of modern physics: why time seems to have a direction. In our experience, time always flows forward. We grow older, never younger. A glass shatters but never leaps back together. The universe expands rather than contracts. This arrow of time has long been linked to entropy, the tendency of systems to move from order to disorder. But if strings are the foundation of everything, then maybe this arrow isn't just about entropy. Maybe it's about the way the vibrations of the universe unfold, like the gradual development of a symphony that can only be played forward, never backward. String theory even opens the door to the idea that time could behave differently in other regions of the cosmos, or even in other universes. If there are extra dimensions hidden within the fabric of reality, and if strings vibrate differently in those dimensions, then perhaps time flows differently there or doesn't exist at all in the way we know it. In one universe, time might move more slowly. In another, it might loop back on itself. In yet another, it might not exist as a separate concept at all. This also raises a fascinating thought about our place in the universe. If time is part of the music of strings, then we're not just moving through time. We're woven into it. Our lives are strands of vibration that resonate within this cosmic rhythm. Every heartbeat, every moment, every thought is part of that same universal timing, emerging from the same deep structure that gives rise to matter, energy, and space itself. And yet, for all this strangeness, we still live inside the familiar experience of time. We still see the sun rise and set. We still count the minutes and hours. And maybe that's the most remarkable thing of all. The universe has taken this incredibly abstract, high-dimensional vibration and turned it into something we can feel. When we look at a clock or watch a shadow stretch across the ground, we're witnessing the surface-level expression of something unimaginably deep, the rhythm of the strings that make up reality. So perhaps time isn't just a background feature of the universe. Perhaps it's the ultimate melody, the one we're all following without even realizing it. And if we could ever truly hear it, if we could listen to the way the strings of the universe hum and resonate, we might find that time isn't just passing us by. It's carrying us forward, like a current in an endless cosmic song. If string theory is right, then every particle, every force, every speck of matter, and even space and time itself comes from the vibration of tiny unseen strings. But this raises a question that is almost unsettling in its simplicity. What if the strings stopped vibrating? What would happen if the music of the universe fell silent? To answer that, we need to think about what vibration means in this context. In string theory, vibration isn't just motion, it's existence itself. An electron is an electron because its string vibrates in a certain way. A photon is a photon because its string oscillates in a different pattern. If those vibrations ceased, those particles would no longer be what they are. They might not be anything at all. This is hard to wrap our minds around because we're so used to imagining the world in terms of objects. We picture particles like little marbles, solid and enduring. But in string theory, the strings are not simply things. They are events. They are processes. Their vibration is what defines them. Take away the vibration, and the string isn't really a string anymore. It's nothing. It's like plucking a guitar string and then suddenly muting it. The note stops, and in that instant, there is silence. Except in the case of the universe, that silence wouldn't just be the absence of sound. It would be the absence of everything. But here's the strange part. The strings of the universe can never truly be silent. Even in what we call empty space, the quantum vacuum is buzzing with energy. Particles flicker into and out of existence. Strings hum at their lowest possible vibration, a fundamental level that can't be reduced any further. This is sometimes called the 0-point energy of the universe, and it means that even the quietest parts of reality are never truly still. And yet, imagining total silence can be useful because it shows us how deeply vibration is tied to reality itself. Without it, there would be no particles, no forces, no space or time. There would be no stage for anything to happen on, no notes to play, no music at all. Silence, in the deepest sense, would mean nothingness. This leads to another fascinating thought. If the universe is defined by vibration, then maybe silence isn't the absence of sound or motion, but the absence of being. It would be like turning off the cosmic instrument altogether. And this makes the hum of existence, the fact that strings are always vibrating, that much more extraordinary. It means that the universe doesn't just exist, it persists, sustained by a ceaseless underlying motion that never stops. Now, some versions of string theory and related theories like M theory suggest that there might be multiple ground states of reality, different ways the strings could vibrate, each one creating a different version of the universe. In one of these hypothetical universes, the strings might be in a kind of stable, minimal vibration that we could think of as almost silent compared to ours. If that's the case, then maybe there are realities where the music of existence plays very differently, where what we consider matter, space and time don't exist in any familiar form. And here's where it gets even stranger. Some physicists have speculated that at the very beginning of our universe, before time as we know it began, there might have been a state of perfect symmetry, a kind of silent state where nothing was yet distinct. No particles, no forces, no directions. And then something broke that silence. The strings began to vibrate, and in that first, unimaginably small fraction of a second, reality came into being. In this view, the universe is the sound of silence breaking. But silence isn't gone entirely. Black holes, for example, come eerily close to it. When matter falls into a black hole, it gets drawn toward the singularity, where space and time become infinitely curved. If string theory is correct, those strings might be stretched and distorted in ways that almost extinguish their normal vibrations, creating a kind of frozen, timeless region. What happens there is still one of the biggest mysteries in physics, but some have suggested it could be as close as we'll ever come to a silent universe. And then there's the far future. Physicists predict that one day, in the unimaginably distant future, the stars will burn out, galaxies will fade, matter itself may decay. If that happens, the universe might approach a kind of quiet, an endless, cold, dark expanse where the strings vibrate only at their lowest energy state. It wouldn't be true silence, not exactly, but it would be close. A universe where the music has slowed to a single, endless, almost inaudible hum. And yet, even in that far-off quiet, there's something comforting. Because if the strings can never truly stop vibrating, then the universe never truly dies. It keeps humming, softly, invisibly, endlessly. And maybe, just maybe, that hum is what keeps reality from ever slipping back into nothing. So perhaps silence isn't the end. Perhaps it's just another movement in the cosmic song, one so slow and deep that we can't hear it yet. If the universe is a song, then maybe it isn't the only one. Maybe what we call the universe is just a single melody in an endless concert of realities, each one playing its own tune, each one built from its own vibrating strings. This is the idea of the multiverse, a vast collection of universes, each with its own laws, dimensions, and rhythms of existence. And if string theory is correct, this isn't just speculation. It could be a natural consequence of the way reality is built. String theory doesn't just describe one possible universe. Its equations allow for many. In fact, when scientists first began exploring the mathematics of string theory, they discovered that there wasn't just one solution. there were countless solutions. Each solution corresponded to a different way the strings could vibrate, a different configuration of hidden dimensions, and a different set of physical laws. It was as if the universe wasn't a single song, but an entire orchestra of possibilities, each playing its own variation on the cosmic theme. Some physicists estimate that there could be as many as 10,500 possible universes allowed by string theory. That number is so large it's almost meaningless. It's far greater than the number of atoms in our universe. In this multiverse picture, every universe is like its own concert hall, with its own instruments, its own tuning, and its own melody. Some universes might be familiar, differing only slightly from ours. Maybe in one of them, gravity is just a little stronger, or light travels just a bit faster. But others could be so radically different that they would be unrecognizable, alien places where even the concept of matter as we know it doesn't exist. And yet, they would all be part of the same grand composition, different songs in the same cosmic symphony. The idea of the multiverse raises a question that is as humbling as it is staggering. Why are we in this universe and not another? Why are the strings here vibrating in just the right way to give us stars, planets, and life? If there are countless universes, then maybe it's not surprising at all. Maybe we simply live in one of the universes where the vibrations happen to produce conditions that allow us to exist. In other universes, where the strings hum in different patterns, there might be no galaxies, no stars, no atoms, nothing that looks like our reality at all. This concept is sometimes called the anthropic principle, the idea that we observe this particular universe simply because it's one of the rare universes where observers like us can exist. It's not that our universe is special, it's just one room in a near-infinite concert hall, and we happen to be sitting where the music makes sense to us. But there's another, deeper possibility. If all of these universes exist, are they truly separate? Or are they, in some hidden way, connected? Some versions of string theory suggest that universes might not be completely isolated. Instead, they could be like different notes resonating on the same instrument. The strings that make up one universe could, under certain extreme conditions, influence or even connect with the strings of another. If this is true, then the multiverse isn't just a collection of disconnected realities. It's a vast interwoven structure, a cosmic concert where each hall, each universe, is part of a greater, unified score. And here's where things get truly extraordinary. If these universes are connected, it might be possible, at least in principle, to hear the faint echoes of other realities. Some physicists have speculated that certain anomalies in the cosmic microwave background, the afterglow of the Big Bang, might be the result of collisions between our universe and others. These would be like faint vibrations bleeding through the walls of our own cosmic concert hall, hints that there are other melodies being played just beyond the edge of our perception. Even if we never detect those echoes, the multiverse changes the way we see ourselves. It means that our universe is not the entire story. It's just one performance, one arrangement of the cosmic strings among countless others. And if that's true, then perhaps the most remarkable thing isn't that our universe exists, it's that it's one song we can actually hear. Yet for all its vastness, this concept doesn't diminish our place in the cosmos. In fact, it makes it richer. Because if the multiverse is real, then everything we know, every star, every atom, every vibration, is part of a far grander stage than we ever imagined. And somewhere, beyond the limits of our vision, other universes are playing their own music. We'll never hear them directly, but maybe that's not the point. Maybe it's enough to know that the concert is bigger than we thought, and that our melody, however small, is part of something infinite. So when we talk about the multiverse, we're not just talking about physics, we're talking about possibility itself. And in a universe built on vibration, possibility is never truly silent. Every note that can be played is played, somewhere in one of those infinite halls. There's a moment when you follow string theory far enough where you begin to wonder if we're still doing science at all, or if we've stepped into something closer to philosophy. After all, when you're talking about 11 hidden dimensions, vibrating strings smaller than anything we can ever hope to observe, and entire universes beyond our reach, it starts to feel like we've left the laboratory behind and wandered into the realm of thought. And yet, physicists keep pushing forward. This tension between physics and philosophy has always been there. Science begins with what we can see, measure, and test. It builds from experiment, from observation, from things that can be confirmed in the real world. But the deeper we've gone, the stranger the universe has become. Atoms once seemed unthinkably small, until we discovered the particles within them. Space and time once seemed absolute, until relativity showed us that they bend and stretch. Now, string theory asks us to go even further, to imagine that what we see is just a faint surface of something vastly more intricate. But if we can't prove it, if we can't test it, then is it really physics? Or are we simply constructing elegant stories about the universe because we like the way they sound? It's a fair question, and one that even scientists argue about. Critics of string theory often point to its lack of direct experimental evidence. They argue that a theory that can't be tested isn't science at all, no matter how beautiful the math is. After all, physics has always been grounded in the idea that if you propose something about the universe, you should be able to prove it. And yet, there's another side to this. Historically, many of the biggest breakthroughs in science began as ideas that couldn't be tested at the time. When Einstein proposed general relativity, there was no immediate way to prove that massive objects bend space-time. It took years for the technology and experiments to catch up. When quantum mechanics was first developed, it seemed like an abstract, almost philosophical framework, until it became the foundation of nearly every modern technology. So perhaps string theory isn't the end of science. Perhaps it's simply the beginning of a new phase of it, one that stretches the boundary between physics and philosophy until the line between them begins to blur. Because when you think about it, the universe doesn't care about our labels. It doesn't care whether we call an idea science or philosophy. It simply is. And if string theory offers a glimpse of how it works, if it shows us a universe woven from vibrations and hidden dimensions, then perhaps that's enough reason to take it seriously, even if proof is still out of reach. There's also a deeper point here, one that goes beyond experiments and equations. String theory forces us to confront questions that science has often avoided. If reality is made of vibrating strings, then why do the strings vibrate at all? Why these vibrations and not others? Why is there something rather than nothing? These are questions that feel philosophical because they dig into the roots of existence itself, into the why behind the how. And maybe that's where physics and philosophy naturally meet, at the edge of what we can know, staring out at what we can only imagine. But it's not all speculation. Even if we can't directly detect strings, string theory has given physicists powerful tools for understanding other areas of science. It's helped explain the mathematics of black holes, inspired new research in quantum field theory, and even influenced our understanding of the early universe. In this sense, it's more than just philosophy. It's a framework that's already shaping the way we explore reality. Still, there's no denying the mystery of it. Maybe that's why string theory has such a hold on the imagination. It isn't just a theory, it's a story. It tells us that the universe is music, that everything is connected, and that beneath the surface of the ordinary world is a hidden structure more beautiful than anything we've yet seen. So is it physics? Or is it philosophy? Maybe it's both. Maybe it's what happens when physics grows so ambitious, so daring, that it begins to ask the same questions philosophers have asked for thousands of years, only now armed with equations sharp enough to cut through the darkness. And maybe that's the point. Because at its best, science has never just been about predicting the next decimal place, or building the next piece of technology. It's about wonder. It's about looking at the universe and refusing to accept that what we see is all there is. And if string theory pushes us to imagine bigger, to think deeper, then whether it turns out to be true or not, it's already done something extraordinary. If you've ever listened to a perfectly played piece of music, you know there's something almost mathematical about it. Each note falls into place with precision. Each rhythm aligns in a way that feels inevitable. And maybe that's no accident. Mathematics and music share a deep connection, and nowhere is that connection more profound than in the way the universe itself seems to be built. For centuries, mathematics has been the language of physics. From the paths of planets to the behaviour of particles, every law of nature we've discovered can be expressed in numbers and equations. But string theory takes this relationship further. It doesn't just use math to describe reality. It suggests that mathematics may be the very foundation of reality. In string theory, the universe is not made of little solid objects. It's made of vibrations, and those vibrations follow precise mathematical patterns. Each string has its own frequency, its own mode of oscillation, and those frequencies determine everything. The particles that exist, the forces that act between them, even the shape of space and time itself. This is where the beauty of string theory lies. If you strip away all the complexity, what you're left with is an elegant idea. Reality is mathematics in motion. Every particle is an equation turned into a vibration. Every force is a mathematical relationship expressed through the way strings move and interact. And we, along with the stars, galaxies, and everything else, are part of that same grand calculation. But what does it mean for mathematics to be so deeply embedded in the universe? Is math something we invented, or something we discovered? This is one of the deepest questions in both physics and philosophy. If mathematics is merely a tool we created, then it's astonishing that it maps so perfectly onto the structure of reality. If, on the other hand, mathematics is something that exists independently of us, then perhaps the universe is not just described by math, it is math. String theory leans toward the latter view. It suggests that the universe isn't simply a physical thing that happens to obey mathematical laws. Instead, it might be that the laws themselves are the universe. Matter, energy, space, and time might be nothing more than the physical manifestations of deeper mathematical truths. Consider the extra dimensions predicted by string theory. They aren't just theoretical curiosities, they're required by the math. Without them, the equations don't work. And when physicists follow the math, it doesn't just lead to one universe, it leads to an entire landscape of possible universes, each one a different solution to the same underlying equations. It's as if mathematics isn't simply a language for describing the cosmos, it's the score the cosmos is playing. And just as in music, even small changes in that score can create entirely different melodies. If a string vibrates slightly differently, it creates a different particle. Change the mathematical structure of a dimension, and you could create a universe where gravity is stronger, or where atoms never form, or where time itself behaves in ways we can barely imagine. But here's the part that might be most astonishing. Mathematics has a habit of predicting things before we ever see them. Einstein's equations predicted black holes before anyone had observed one. Quantum theory predicted particles long before experiments confirmed them. And in the same way, string theory's mathematics has led physicists to new insights, ideas about gravity, quantum entanglement, and the deep structure of space-time that may one day be confirmed. So when we say mathematics composes reality, we're not just speaking metaphorically. We're talking about the possibility that the universe itself is a kind of mathematical object, one that exists not because it was created in some physical sense, but because it had to exist, because the math allowed it. And that's where string theory becomes something almost unsettling in its elegance. If everything is vibration, and every vibration follows mathematical rules, then maybe the universe has no choice but to be what it is. Maybe it's like a piece of music that, once you write the first few notes, must follow a certain structure. Maybe the reason we're here at all is because this is the only way the math could play out. Of course, this raises as many questions as it answers. Why this mathematics and not some other? Why do the strings vibrate in exactly these ways? But even if we don't know the answers, there's something profoundly beautiful about the idea that beneath all the complexity of reality lies a kind of pure, crystalline order, a mathematical framework so deep and intricate that it gives rise to everything. So the next time you think of the universe, try to imagine it not as a machine or a collection of objects, but as a piece of music written in numbers. Every particle, every star, every breath you take is part of that composition. And if string theory is correct, then the song isn't just being played, it's still being written, one equation at a time. Science is a conversation between theory and experiment, a dance that has played out throughout history. Theories propose explanations, bold and beautiful, and experiments test those ideas against reality. Sometimes experiments confirm what we suspect, and other times they surprise us, forcing us to rethink everything. String theory sits at the cutting edge of this dance, an elegant framework waiting for experiments to catch up and reveal whether its bold predictions reflect the universe we live in. For decades, string theory has been primarily mathematical, a realm of equations and possibilities rather than direct observation. The strings it describes are incredibly small, far beyond the reach of any current technology. The energy scales required to probe them directly are unimaginably high, far greater than what even our most powerful particle accelerators can achieve. So the challenge has been, how do you test a theory about things you can't see? Scientists have devised clever indirect ways to look for signs of string theory in our universe. One approach is to search for evidence of the extra dimensions that string theory predicts. Although these dimensions are hidden and compactified, curled up so tightly that we can't observe them directly, they might still influence the behavior of particles and forces. For example, the presence of extra dimensions could alter the properties of gravity at very small scales. Researchers have conducted experiments to test whether gravity behaves differently than expected at tiny distances, but so far no deviations have been found. The search continues, with more sensitive experiments planned. Another avenue involves the study of cosmic phenomena. The early universe, shortly after the Big Bang, was an extreme environment where the energies and densities were unimaginably high, perhaps high enough to reveal the effects of vibrating strings. Cosmologists look to the cosmic microwave background, the afterglow of the Big Bang, for subtle patterns that might betray the fingerprints of string theory. Tiny fluctuations in this ancient radiation could carry information about the universe's earliest moments, including the behavior of strings. Future missions with more precise measurements could shed light on this. Gravitational waves, ripples in the fabric of space-time caused by cataclysmic events like merging black holes, have opened a new window into the cosmos. These waves, first directly detected in 2015, might carry clues about the structure of space-time at the smallest scales. If string theory is correct, the vibrations of strings could leave subtle signatures in the gravitational waves we observe. Scientists are developing ways to analyze gravitational wave data for such effects, hoping to catch whispers of the string's cosmic dance. Particle physics experiments also play a role. The Large Hadron Collider, SLHC, and other accelerators smash particles together at incredible energies, hoping to create new particles or phenomena predicted by theories beyond the standard model of physics. Some versions of string theory predict exotic particles or behaviors that could show up in these collisions. So far, the LHC hasn't found direct evidence for string theory, but it has pushed the boundaries, ruling out some possibilities and guiding theorists toward more refined models. The gap between theory and experiment is daunting, but it's not unprecedented. The history of science is full of ideas that took decades or even centuries to be tested. When the concept of atoms was first proposed, it was a philosophical idea without experimental proof. It took the development of new technologies and experiments to confirm their existence. Similarly, the predictions of general relativity were confirmed only years after Einstein proposed the theory, when an eclipse allowed scientists to observe the bending of starlight. String theory, in this sense, is at a similar crossroads. It's a theory rich in mathematical beauty and potential, but it awaits experimental validation. The hope is that future advances in particle physics, cosmology, quantum computing, or entirely new fields will provide the tools needed to test its predictions more directly. There's also a sense in which experiments have already caught up to string theory in unexpected ways. The mathematics developed for string theory has found applications in other areas of physics, such as condensed matter physics and quantum information theory. Insights from string theory have helped scientists understand phenomena like superconductivity and entanglement better, showing that even if the strings themselves remain hidden, the theory's influence reaches far. So while string theory's ultimate test may lie in the future, the dialogue between theory and experiment continues. Each new discovery, each new piece of data, refines our understanding, shaping the theory and guiding the search. And perhaps one day, when experiments catch up, we'll finally hear the full melody of the strings, confirming a vision of the universe as a vast, vibrating symphony, resonating through dimensions beyond our imagination. If string theory is right, then we're not just living in a universe made of strings, we are made of them. Every atom in our bodies, every particle in our blood, every flicker of thought in our minds arises from the vibrations of these invisible threads. Life, in this view, is not something separate from the cosmos. It is one of the melodies that the universe plays. It's a humbling thought. For most of human history, we saw ourselves as separate from the great machinery of the cosmos, as observers looking out at a distant universe. But string theory invites us to see it differently. There is no out there and in here. There's only one vast network of vibration, and we are part of it, as inseparable from the rest of the universe as a single note is from the song it belongs to. Think about it this way. Your body is a collection of atoms, and each of those atoms is built from particles, electrons, quarks, and the rest. In string theory, each of those particles is a particular pattern of vibration. So in a very real sense, you are a symphony of strings, a living chord in the music of the cosmos. The rhythm of your heartbeat, the firing of your neurons, the flow of blood through your veins, all of it happens within a world already vibrating at the deepest level imaginable. And if everything is vibration, then life might be nothing more and nothing less than a special arrangement of those vibrations. Perhaps what we call biology is simply one of the many ways that the universe organizes its music, like a motif woven into a larger composition. This view changes how we might think about our place in the cosmos. If we are part of the music, then the universe is not indifferent to us in the way we sometimes imagine. It doesn't have to care, but it also doesn't have to be separate. We exist because the strings vibrate in just the right way, because the hidden dimensions are folded just so, because the laws of physics align to create a world where matter can form, where stars can burn, and where life can emerge. In another universe, with different vibrations, there might be no life at all. Or there might be forms of life so strange that we wouldn't recognize them. Not carbon-based organisms, but patterns of vibration that exist in ways we can't even imagine. If string theory is true, then life, like everything else, is written into the music. But not just our kind of life, all kinds. Life could be as varied as the infinite ways strings can hum. This also raises a profound question. If the universe is a symphony of strings, what role do we play? Are we just listeners, hearing the music as it unfolds, or are we part of the orchestra, adding our own faint notes to the cosmic song? Some physicists and philosophers have wondered if consciousness itself could be linked to this deep structure. Perhaps what we experience as thought is, in some sense another form of vibration, an emergent resonance of the brain, born out of the same fundamental patterns that give rise to matter and energy. It's speculative, but it's a strangely comforting idea that our awareness, our ability to wonder about the universe, is not an accident. It is part of the music too. And this brings us to an even deeper possibility. What if life is not just a byproduct of the universe, but something the universe does naturally? If vibrating strings give rise to particles, and particles give rise to chemistry, and chemistry gives rise to biology, then life may be woven into the structure of reality from the beginning. Perhaps the universe has been tuned for it, not deliberately, but simply because this is what happens when strings hum in the right way. In this sense, life isn't separate from physics. It's physics, expressed in one of its most intricate forms. The same laws that govern black holes and galaxies also govern the beating of your heart. The same vibrations that create stars also create you. And when you think about it that way, it becomes hard to feel entirely alone in the cosmos. Because if the universe is music, then everything, every star, every tree, every fleeting moment of your life is part of the same performance. We are not spectators watching from the balcony. We are notes in the song, resonating quietly in a universe that has been singing since the beginning of time. And maybe that's what it means to live in a world of strings. It's not just that we are surrounded by a vibrating cosmos. It's that we are woven into it, inseparable from it, part of a melody that was playing long before we were here and will keep playing long after. And yet the most extraordinary thing is this: somehow, impossibly, we can listen. Consciousness is the quiet mystery at the center of everything. We live every moment of our lives inside it, yet we still don't fully understand what it is or where it comes from. Science has explained how neurons fire, how signals move through the brain, how chemistry and biology shape thought. But none of this quite explains why there's an us inside it all, why the universe looks out at itself through our eyes and wonders what it is. And when you place that question inside the framework of string theory, the mystery only deepens. If the universe is built from vibrating strings, and if everything we see and touch is born from these vibrations, then what is consciousness? Is it something separate from the cosmic music, or is it one of its notes? One way to think about it is this: if every particle in our bodies, every atom in our brains is made of strings vibrating at specific frequencies, then consciousness must also be tied to these vibrations. It doesn't float above them. It emerges from them. In this view, awareness might be a resonance, an incredibly complex pattern formed by countless strings vibrating in harmony, not just in our brains, but throughout the matter that makes us. This isn't just poetic musing. Even in neuroscience, researchers are beginning to explore the idea that consciousness might be connected to patterns of oscillation. Brain waves, those rhythmic pulses of electrical activity, are measurable vibrations. When we think, dream, or focus deeply, the rhythm of these waves changes. And while this is happening at a biological level, string theory suggests that there might be something even deeper beneath it, an underlying hum that stretches down to the fundamental fabric of the universe. What if consciousness is what happens when the universe's vibrations become aware of themselves? There's a strange elegance to that thought. After all, if the universe is a vast symphony of strings, then we are not separate from it. We are made of the same vibrating matter and energy as everything else. The music of the cosmos doesn't just surround us, it plays through us. And perhaps consciousness is what it feels like from the inside when a small part of that music starts to listen. This might also explain why consciousness is so hard to pin down. If it is an emergent property of vibration, a pattern arising from the deepest levels of reality, it wouldn't be located in any single part of the brain or any single atom. It would be distributed, like a chord spread across many strings. And if that's true, it could mean that consciousness isn't unique to us. If vibration is fundamental, and if awareness can emerge from complex arrangements of vibration, then perhaps the universe is filled with forms of consciousness we can't recognize. Alien patterns of awareness built on different kinds of matter, different laws, or even different dimensions. And what about the universe itself? If every string hums, and if those vibrations connect across dimensions, could the cosmos itself be a kind of awareness? Not a mind like ours, but something vaster and stranger. A field of resonance so immense that every conscious being is just a flicker within it. These are not questions we can answer yet. Maybe they're not even questions we're ready to answer, but they follow naturally from the logic of a universe built on vibration. If the cosmos is music, then perhaps we're not separate from the song. We are the part of it that can hear. And maybe that is why, when we sit in silence and let the world fall quiet around us, there is sometimes a sense of something deeper, a hum beneath the noise, a feeling that we are not just in the universe but of it. It might be nothing, it might just be neurons firing, or it might be the faintest echo of the cosmic vibration, the one that has been playing since the first strings began to move. In the end, whether consciousness is just a biological phenomenon or something woven into the structure of the universe, string theory invites us to see it differently, not as an accident, not as a separate, isolated spark, but as another part of the music. And perhaps that's the most extraordinary thing of all. In a universe made of vibration, awareness is the moment the music starts listening to itself. If string theory is true, then everything is music. Not metaphorically, not symbolically, literally. Every particle, every force, every thread of space-time is a note, a vibration, a soundless hum in the deepest structure of reality. But if that's what the universe is, then what does that make us? Are we instruments playing out the melodies written into our very being? Or are we simply part of the song, like a single harmony sustained within a grander composition? Maybe we're both. From the smallest scale, we are vibrations stacked upon vibrations. Quarks hum together to form protons and neutrons. Electrons orbit, their energy levels determined by quantum rules that are themselves expressions of vibration. Atoms join to make molecules, molecules bind into cells, and those cells build us. Layer upon layer, pattern upon pattern, until what emerges is not just a body, but a presence. In this sense, we are arrangements, living chords struck from the same strings that weave galaxies and stars. The frequencies that shape matter also shape us, and in that way, there is no boundary between our existence and the universe's deeper music. We are not separate listeners to this song. We are part of it, vibrating in time with a rhythm older than the earth itself. But then, there is something about us that goes beyond simple vibration. We can hear the music. We can wonder about it. A rock or a tree might resonate with the same fundamental strings, but it does not sit awake at night and ask why those strings exist. We do. And maybe that is our role in this cosmic composition. To give the music an ear. To turn the silent hum of the universe into meaning, to listen to it and reflect it back. In that sense, we are not just part of the song, we are its echo. This is what makes us extraordinary. We are built from the same vibrating strings as everything else, but those strings in us have formed a pattern complex enough to ask what they are. We are the music wondering about itself, and if that's true, then every moment of human existence, every thought, every feeling, is not separate from the universe's deeper structure but is tied to it. When you speak, the air vibrates. When you listen, tiny strings in your body respond. When you laugh or cry or dream, you're riding on waves that began long before you existed, waves born in the hidden dimensions where the universe first took shape. So if everything is music, what are we? Maybe we are notes that know they are notes. Maybe we're not just part of the melody, but a way for the melody to become aware of itself. And there's something profoundly comforting in that. Because if this is true, then we are never truly separate. Not from each other, not from the stars, not even from the strings that hold space and time together. We are connected through the deepest resonance there is, the fundamental vibration of reality itself. And if that's the case, then perhaps the universe isn't a cold, indifferent void after all. Perhaps it's a living score, and we, our lives, our choices, are fleeting moments of wonder, are lines of music written into it, brief but meaningful, no less a part of the song than the stars themselves. So what are we? We are music. Quiet music, maybe. Temporary music. But music nonetheless. And if we could ever hear it in full, if we could listen past the noise of our daily lives and truly feel the vibration that underlies it all, we might realize we've been playing along all this time. There's a stillness at the heart of music, a silence that holds the sound together. Without it, the notes would blur into noise. It's the space between vibrations that gives the melody its shape, the pause that makes the next sound feel alive. Maybe the universe works the same way. If string theory is right, reality is music. Every particle is a note, every force is a chord, every dimension is a hidden harmony. But even in that grand cosmic symphony, there must be quiet, the deep, steady silence that holds it all. And perhaps, in that silence, there's something for us too. We spend our lives listening to the loudest parts of existence, the motion of planets, the hum of cities, the relentless ticking of time. But beneath it, there is always a softer layer, a hum so deep that we can't hear it with our ears, but maybe feel it in the pauses, those fleeting moments where everything seems to stop, and all that's left is the vastness of the world around us. String theory doesn't just describe a universe of motion, it hints at the stillness inside that motion. The tiny strings vibrate, yes, but even their movement happens against a backdrop of something quiet, something stable. The silence between the notes is not empty. It's what allows the music to exist at all. And maybe that's the part we forget. We chase the sound, the answers, the theories, the discoveries. But the silence is just as much a part of the song. It's in the pause between one vibration and the next. It's in the spaces that separate galaxies and the moments of stillness in our own lives, when we stop long enough to feel the hum of existence around us. Because if the universe really is music, then we're not only made of its notes, we're held by its quiet. So tonight, if you close your eyes and let the noise fade, imagine the strings beneath it all. Imagine their hum, so deep and constant that it doesn't need to be heard to be real. Imagine the music of the cosmos not just as sound, but as presence, filling every atom, every star, every corner of reality. And then, in that silence between the notes, rest there for a moment. Because that silence, as much as the music itself, is where the universe lives. And it's where we live too, small, temporary, but part of something vast and unbroken. The song goes on, always. And maybe, if you listen closely enough, you'll realize you've been hearing it all along. Thank you for drifting through this with me tonight. If you've made it this far, maybe you felt it too. That faint hum beneath everything. The quiet suggestion that the universe is not cold machinery, but something alive with motion and resonance. If this journey left you with more questions than answers, that's exactly how it should be. The music of the cosmos isn't meant to be solved. It's meant to be heard, slowly, patiently, one vibration at a time. So wherever you are, let the sound of it carry you. Let it soften the edges of your thoughts. And if you'd like to keep exploring with me, these quiet, impossible ideas, stay here. Like, subscribe, or simply return when you need a place to rest inside the questions. Because the music isn't going anywhere. It's been playing since the beginning, and it will keep playing long after us. For now, let's just listen. Good night.